All right, good morning, everyone. For the people in the back, we have some premium seating right here up front. If you want to sit on the first row, we have one spot left, I think. So there's some other spots on the second and third row. So if you want to sit down, don't hesitate, just come up. And we're going to talk about common API security pitfalls. So this talk is going to be an overview of a lot of problems that can happen in an API, a lot of problems you might have in your API, and a lot of problems I'm going to try to help you solve in your APIs. And I started talking about this actually quite a long time ago, in 2017, when they added something to the OWASP Top 10. So the OWASP Top 10 is a list of the 10 most dangerous vulnerabilities in web applications. And they make this list every couple of years, and in 2017 they proposed to add underprotected APIs to that list of vulnerabilities. Some things happened in the community. A lot of people were very discontent with what the top 10 has become, and the whole project shifted gears a bit, and this disappeared in the final version. But it didn't matter because the seed was planted. People realized, like, holy crap, we're building all these API-based applications, and this is a real problem. We need to start thinking about security specifically for that, and that's why last year they launched the API security project in OWASP as well. And this API security project focuses on everything API security related. They even built a separate top 10 for issues about API security. So if you're interested in API security, if you want to get started with API security, I suggest to take a look at that because it's a treasure trove of information. I'm not going to talk about the top 10 of API security issues. Some of them will be in there, some of them might not be. I'm going to talk about my own experience. I'm going to talk about what I see when I talk to developers, when I teach developers about security, or when I look at their systems. I encounter often the same things, which is what I distilled into this API security pitfalls talk. Just to make sure that we're on the same page, I want to sketch a little, totally not official architecture diagram. So what we're doing is we're building an application. Today it's going to be typically a web application, in a lot of cases a front end. So you're loading your front end, your client-side JavaScript-based application, whether it's Angular or React or Vue, it doesn't matter, you're bootstrapping that in the browser. That's step one. At that moment you have an empty shell. You have something that doesn't really do anything useful because typically you need backend systems to make that work. And that backend system is going to be your API. It's going to be fetching data from an API, rendering, displaying that, and when you perform an operation, it's going to push that operation back to the API to actually persist that later on. We're going to talk about the API part. We're not going to talk about the front-end security part, which also means that in this case, it's also very relevant for people building other types of clients. If you build a mobile client or a desktop application or whatever, if it's backed by an API, I can guarantee that almost every one of these issues we're going to talk about is going to be relevant. I didn't count them, so I have no idea how many we're going to cover, but that gives me flexibility to cut it short when we're running late. But we're going to be totally fine. This image is a good starting point. Because a lot of people, well, sometimes you have full stack developers, sometimes you have the split between front end and back end, but a lot of people think about this image as a whole. While actually only the top part is usually relevant for security, because the top part is where the things happen, where the data is, where the operations happen. And a very good example is Tinder. You can swipe left and right for looking for a partner, totally based on appearances, so it's absolutely not what we stand for as a society, but sure, it's probably very useful. By the way, everything I'm telling you now is totally anecdotal, because I have a wife, and otherwise she would be very, very displeased with my behavior. But as it turns out, apparently, you can also see who likes you. So other people can see your profile, and they can, when of course they like you, the app is trying to sell you a premium subscription by showing you blurred images like, hey, these people like you want to see what they look like, right? So why not pay us and we'll get you access to that data. But it turns out that the blurring of the images is a front-end operation. The mobile app just pulls in the image and blurs it and then shows it to you. So of course, if you know a bit about computers, you're like, do I want to pay for that? No, let's just spend a lot of time figuring out how it works, and you'll find the API call that you can actually use to get that image. And with that, you can actually get the image, and so on and so on. So somebody else figured this out. They analyzed the web application, figured out the API endpoints, mimicked the call coming from the iOS application, and they got the images just like that. And that brings us to the first important pitfall. Your API is a real attack surface. It's not the front end. Yes, there are some security things you need to address in front ends, but usually it's going to be about your API. That's where you should focus most of your efforts when you look for security problems. And a lot of APIs overexpose data. Not only images, but just fetching like full JSON objects and then displaying 3 fields in the front end. And yeah, everything else is hidden, right? Well, not if somebody figures out what the API calls are, what the traffic looks like, they can grab all of that data just like that. So that's definitely one thing to keep in mind. Also sets a very good theme. We're going to talk about a lot of authorization issues. Because in security, it often comes down to authorization, to preventing somebody from doing something they're not supposed to be doing, which is authorization. We need some things to make that work, and we'll talk about that later. First, another authorization problem. I really like these cases, not to make fun of companies getting it wrong, but to illustrate you that these are real things. Because when I talk about these things, people are like, yeah, nobody does that in practice. Like, come on, we know better than to do that. Well, apparently not. What happened here? T-Mobile, mobile phone operator, they can give you access to your account. You want to access your account information, it's going to be an API call with your phone number. Phone number is a unique identifier for your account. Makes sense since cell phone numbers are unique and linked to your account, so why not? The problem here is called insecure direct object references. It's an old problem and has been around for a while. And what the problem actually means is that if I substitute my phone number for your phone number, I'm going to get your account information, just like that. Then I figure out what his phone number is, and bam, I got his account information, and so on and so on. And what they actually did check is whether you were authenticated, but they never checked if you were the actual person, the owner of that account, and were supposed to access that information. It's an insecure object reference. Happened to T-Mobile, happened to Telefonica in Spain, to AT&T in the US, and to Verizon in the US as well. All of the phone companies apparently have a very similar vulnerability. And it happens in other cases as well. Insurance documents linked to by numbers, a very long identifier in the URL, and when it starts with 0000204, somebody might try 0000203, and boom, there you go. Other document, and so on, and you can start enumerating that. Used to be a problem in old web apps, we have the same thing in APIs. Just like that, we call it differently, it's called broken object level access control, but it's the same essential problem under the hood. And these things are really, really common. I can guarantee you that in this room, 5 to 10 people, if they go look at their APIs on Monday, they will find this problem. Absolutely that common. And why does it exist? Because we build applications with tutorials. We learn about REST APIs in Node in 10 minutes. And in 10 minutes, there's not going to be any security in there, I can tell you that. It takes a lot longer to talk about security. But this is okay because it's about the REST paradigm. And you learn how to build a to-do application, of course. And it's about fetching tasks, so you can read a task with a task identifier. Here is a request.parameters.task.id. And you can delete tasks with a task identifier. Of course, you send it a delete request, and it will make sure that the task disappears. And when you build a first application, your first API like that is going to be awesome. Like, oh, this is pretty cool. And of course, then you're going to think about users. Like, hey, but I don't have a single user. I have different users. So let's learn about how to do authentication and users and all of these things. And that information, that tutorial, that course is going to talk about how you have to implement authentication checks. Like, is the user logged in? No. Oh, in that case, let's send them a 401. Otherwise, go ahead and perform that operation. And that's exactly what T-Mobile and all the other phone companies also did. But then you have to think further. Then you have to think about who's allowed to access this particular task, who can read it. And you have to implement explicit authorization checks. And these things are often missing because often people don't talk about that, and they're not very easy to implement. It's a very difficult problem to solve. And unless you go to your application and you look for the absence of that code, you're not going to spot this. Yes, with testing, you'll find the fact that somebody should be logged in before they can access that. That's going to be in your test. But unless you thought about this problem explicitly, it's not going to be in your tests, and you might be missing that particular piece of code. And the cases I talked about illustrate that this thing is really, really common. All right. Brings us here, lack of proper authorization. Always check both authentication status and object level access control. Check if the user is allowed to access these things, yes or no. And again, that's not an easy problem to solve. Even in a task manager, like the one I showed you here, this can get complicated really quickly. I use a task manager that I share with my wife, for example. Our full household and life is basically in a to-do application. But that means that deciding if somebody's allowed to read a task means, did this person create that task? Like, okay, that's fine. Or are they part of a shared project which also gives them access to this task, which gets complicated really, really quickly. It's not an easy check to do at a single location in your application. That brings us here. So you're going to get a call to a backend like, hey, I want to fetch this information. And there's going to be some authorization information. We'll talk about that in a second. There might be some custom headers, a token in a header, something like that. And then that call is going to invoke other services in your application architecture. And I'm explicitly or deliberately vague about this, services. Whether it's a microservice or another layer in your monolith application doesn't matter, because this happens in all types of applications. There's all things involved. There's a data access layer, there's maybe a layer to a controller doing something, and so on and so on. And at each of these layers, you typically make authorization checks. Like, is the user logged in? Oh yeah, that's good. Then let's move ahead with this call. And then maybe there, you want to check, oh, this user is allowed to read this task. That's cool. And that part does something else based on different customers and different projects maybe. So there's going to be a customer-specific ID check, and God knows what else, a user-specific ID check or something like that. And all of these checks together, that's your authorization policy. And this is something really interesting, because if I do a security assessment, I'm typically sitting around a table with 5 to 6 of the engineers that built the application, and we talk about how they handled security. And I'm going to ask them, like, hey, if this call comes in, how do you know that this user or application is supposed or allowed to access this particular object? And of the 6 people around the table, 5 people are going to be looking at John, because that's the guy that built this authorization policy. And John is going to be like, oh crap, I'm on the spot now. And you see him thinking like, so this call comes in, so we have a token in the request, so we're going to take this parameter out of the token, and that comes out of the database, and then based on this, so yeah, I think we have discovered. That's the good case. Yeah, this is fine. The bad case is like, oh crap, and they start writing like an authorization rule on the fly, like, let's just update the code to add this. But these things are hard to analyze. They're hard to audit. And if you have a policy like this where only a few people in an organization have the full mental model of that, it's going to be insanely difficult to actually audit that policy. You have no idea what checks are enforced and what checks are not enforced. And if these people are sick or leave the company, nobody knows. And that's why you need a centralized authorization policy. These checks are good as a defense in depth mechanism. Absolutely use them. But preferably you have one place where you can specify an authorization policy. Whether that's in code or a separate declarative policy run by a policy agent doesn't really matter here. But you need to have an auditable, centralized authorization policy. You need to be able to go to one place in your application and say, like, this is what we enforce on incoming API calls. And that will give you a good idea. And that if somebody asks, like, hey, have we covered this particular authorization problem for this particular endpoint, you can go there and see, like, oh, we probably should add that. Or, oh yeah, this is covered, here's the policy. And that's a very good way of making authorization checks. All right. By the way, if you want to grab a copy of the slides, I pushed a tweet out, so you can go to my Twitter feed and grab a full PDF with a lot more slides than what I'm talking about here. So that's definitely a good way to spend your weekend reading about API security. All right. Or just do it Monday. I know, work-life balance, I understand that, so let's do it on Monday. That's also fine. All right. Authorization. Like I said, we're going to talk a lot about authorization. Authorization, or propagating authentication state, that's essentially what we're doing. We're logging in once as a user, and for every subsequent call, we need to know, oh, it's Philippe making the call, so we can make authorization decisions. And this used to be a fairly simple thing to do. You had a client and you had a backend. This is the old days. This is Internet Explorer and a PHP or Perl backend with a MySQL database. Remember those times? Life was a lot simpler back then. Anyway, your application grew. You got a lot more users. Maybe there was like a Firefox user in there, sure. Let's make sure that works as well. But essentially you had a number of clients and a manageable number of backend servers. And that's a typical application model. This is called stateful because the servers typically keep session state. A PHP session ID pointing to a server-side session object, keeping track of state such as, is the user authenticated? Yes. What's his username? Philippe. That's essentially what's going on. In the REST world, this is considered to be evil. Like, no, never ever keep state on a server in a REST world because we have stateless services. Honestly, I don't really agree with that. There's nothing wrong with keeping state right here on backend systems. There's something wrong with writing stateful code, I fully agree. If you write code that behaves differently based on what's in that object, that might not be the right thing to do. But if you're making authorization decisions with server-side state, that works. We know how to do that. We know how to use sticky sessions or session replication on the server. And your engineers if they've been doing web app development for 20 years, they know how to do that. And if you're building a small to medium scale application where you know that you'll have a few hundred users and nothing more, often my recommendation is just use this mechanism. It works. Of course, if you're building something like this, we have a bunch of services, like 20,000 Amazon instances and a gazillion clients, this is probably not going to work very well. And that is not the use case for that anymore. Then you have to move towards these stateless systems, and it makes a lot of sense. But what I see is that a lot of people read about these REST APIs and statelessness, and they look at Twitter. How is Twitter doing things? And then they replicate this in their application. It takes a lot of effort to get it right. We're going to talk about that in a second. A lot of effort to learn about these things, to get it right, only to realize afterwards, like, yeah, we only have 100 users, so why did we do that? What's wrong with our Java session ID in a Spring Boot application? It works. There's modules to actually do that. And it makes a lot of sense in certain applications. So I'm not saying one is better than the other. I'm saying one is a bit easier than the other, sure. But if you want to move from stateful server-side sessions to stateless sessions with tokens probably, do it for the right reasons. Do it for scalability, not because somebody said so that you have to do that in a blog post about how to build your first Angular application. Make sure you think this through. PHP session IDs, probably not sequential and single digit, but you get the idea. This is server-side state. Server-side state lives in this nice server-side environment in memory, which is considered to be a fairly secure environment. If somebody can modify that information, trust me, that's going to be the least of your problems. You're going to be screwed anyway. However, if we move this to the client, the backend becomes stateless, which is awesome, but our data now lives in a very insecure environment where everybody who knows how to open up local storage can start tampering with that information in the browser. It's like, oh, here's a value, authenticated false. Well, let's change that to true and see what happens. I can guarantee you there's APIs out there that are like, oh, you're authenticated. Oh, here's the data. That happened in practice. There's APIs where you can change admin equals false to true, and the API is like, oh, welcome admin. Bam. Just like that. Of course, we know better, so let's not talk about that. But how do you protect that data? You need integrity protection. Absolutely, you need to be able to detect unauthorized changes to this information. You might also need confidentiality because server-side memory, confidential low storage, if you put sensitive information there, healthcare information, financial information, it is considered to be a safe place to keep that information. Client-side storage, not so much. You might be breaking God knows how many regulations by pushing that data into the client. So think about these things in practice. We're going to think about that and learn about that. You're probably going to end up here, a JSON web token, a JOT. And a JOT is, sorry for the sign language people here, the next part is not going to be very straightforward to translate, but try to stick with me. So a JOT is a way to represent JSON data. And we all know what a JOT looks like typically. And a JOT has a header, a payload where the actual data lives, and a signature. And when you get the JOT, you want to grab that data out of here. That data is going to be the useful piece of information that you want to do something with, such as make authorization decisions. Here's a code example of how to do that in Java. And this is a very interesting example because I often show this in my training courses and ask people, what's wrong with this? And you have a group of 20 people in the room, and this happens generally on every occasion, and they're looking at this like, that's interesting. There's probably one meaningful line of code, yet people are like, I know some, I can't really pinpoint it. And there's like one or two persons like, yeah, I think you're just getting the data out, but you're not verifying any integrity. You don't know whether you can trust that data. And they're right. This line 3, the decode function, is simply decoding the payload from base64 to JSON. Well, in this case, to a Java object, actually. This is or a better way to do things. Verifying the signature first before we're getting the data out. The result is the same. In line 6, we get a decoded JOT object, just like we did in line 3, but the implications are a lot more serious here. Because the first code example is extremely vulnerable. Anybody can give you anything they want, and the second is the way to get it right. And I don't blame developers for this because, honestly, we don't read the documentation for every function that we ever call. That's why it should have been called insecure decode or decode without verifying signature. Because that would tell you as a developer like, that's probably not the one I need, and you will be able to find other solutions. This is just an illustration of why moving these things to the client makes things more complicated. Don't mishandle client-side session data, if you want to call it that, or authentication state or authorization state, whatever you want to call it. I honestly don't care about the name. I care about what it represents. And that's exactly what this is about. Don't mishandle that. All right. I'm going to talk about JOTs for a while now. Why? Because they have become the de facto standard to do these things, and there's a lot of things wrong with them, usually. Let's talk about the pretty purple part here, the payload. That's where the actual data lives. That payload often looks like this. I can guarantee you, if you open up Google, or sorry, if you open up DuckDuckGo, I should say, in your Brave browser, which is actually pretty awesome, you can Google for how to do token-based authentication in Angular apps, and you're going to find something like this, like just authenticate the user and push some stuff in a JSON web token and send it to the client, and off we go. And people love it because it's a stateless paradigm. If you look back at your very old PHP application that we all know that you're still running, but that's a different story, it's going to look like this. You're going to get a session ID, a meaningless identifier, and you're going to have to look it up in the database, and then you get some, well, database or memory or Redis cache or whatever, and you're going to get some session data, and you can make your authorization decisions. State on the server, whether it's in a database or whatnot, if you deploy this in different geographical zones, it's not going to work very well. And this new paradigm, that's often called token-based authentication, which is a very incorrect name, but that's, again, not very important here, looks like that. Beautiful, right? No more data stored on a server, no more state to manage or replicate. No, we can simply get it out of the JOT by verifying the signature, and we're good to go. However, when you implement a system like this, you have vastly different properties. Because here you have full control over what's happening. You can control sessions. You know how many active sessions there are. You can kill a session if you want to. You can revoke access to a session, and so on. Here, you have nothing. And especially if you use it as a session, this token that you now have is going to be valid for 8 hours, 12 hours a day. And if somebody loses that token, if somebody steals that token one way or another, you're in a world of trouble because there's no way to kill it. There's no way to even tell the application, like, don't accept this anymore. This one is bad. It doesn't exist. Of course, if you think about this up front, you can build systems. You can build, for example, a list of revoked tokens, a very common approach. Like, what if we give every token an identifier? And then we keep a list of bad identifiers so we know that this one shouldn't be accepted anymore. And you get something like this. So you have your token, and you have a list, a database or a cache or whatever somewhere with a list of known bad identifiers. So you have to go check it every time a token comes in to make sure if it's still valid or not. And that's under the assumption that you kept these identifiers in the first place linked to specific users or specific devices. Because if you don't have that list up front, then this doesn't even work very well. Again, to show you that there's a lot of things wrong with blindly pushing that state to the client. It doesn't work like that. Somebody on the internet called Yuppie has been saying that for a very long time. He wrote a blog post, a very ranty blog post, which is actually very spot on. And of course, people started suggesting solutions like changing keys or keeping lists of revoked identifiers. So he built a very sarcastic flowchart to tell all of them that they're wrong, because everything ends up either in usability problems or security problems. All of them. Brings us, I suggest you read it, it's actually really interesting. Brings us to the takeaway here, don't mistake a JOT for a session. A JOT is just a way to represent data securely by adding integrity protection and confidentiality if you want to, but it doesn't do anything. It's not a session, it's not revocable, and if you want to use JOTs, like OAuth does, you need a whole supporting ecosystem to make them work. That's why OAuth is so complicated, because it ensures that there's a central party in control of issuing tokens and making sure when a token is renewed that they're allowed to get a new token, adding revocability and all of these things into the mix. All right. Back to a JOT. We talked about this a few times. JOTs have integrity protection. They are signed by the issuer, meaning once they're signed, a receiver is able to verify whether the JOT has been changed in between yes or no, which is good. Otherwise, I could change my user ID from 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 to something else, and I would become another person. That's not possible because of a signature. The blue part here is a signature. A few things about signatures. You'll often find them as an HMAC. More on that in a second. Don't use super secret HMAC key as a secret to sign that HMAC. And if you use something else, don't put that on a PowerPoint slide and broadcast that to the world. Again, seems obvious, but people have found production systems using keys copy-pasted from blog posts. Like a blog post explaining how this works, something like super secret HMAC key, copy, paste, production code. Oh yeah, this seems to work very well. Don't do that. Why? Because here's how an HMAC works. An HMAC takes as input the data. In a JOT world, that's the header and the payload, and they're going to push that through an HMAC function, a dedicated cryptographic function that takes a secret key as input, super secret HMAC key, and spits out an HMAC. That HMAC is uniquely linked to this data and this key. And that's what you add to the JOT. That's the blue part in the JOT. You push that out to the client, and everybody's happy. That's how you issue a signed JOT. Then when you receive a JOT, and you get the data and the payload, and you're going to push that through the HMAC function again with the secret key, and out comes an HMAC. And now you can compare these two HMACs. You can compare the original one with the new one. And if they're the same, then you know that the message of the JOT, the data has not been changed in the meantime, since issuing that JOT. And if they did change, maybe somebody added a white space, maybe somebody changed a 0 into a 1, we don't care. If it's not valid, we reject it and we kick it out. And that's how an HMAC works. There's one big elephant on this slide, one big glaring problem. This works perfectly fine in your application. Sorry for targeting you. If you build an application that issues a JOT and receives a JOT, you can verify that signature. Very easy. You use Key Vault to put that secret in, you get it, or you ask the vault to verify that signature and you're done. Awesome. However, if you make friends at a conference and you want to give their application JOTs, they're going to need to verify the integrity of that JOT. So you might be tempted to give them your secret as well. Don't do that. You can never keep a secret more than one application, basically, or one person, unless you kill them, which is a lot harder with applications than with people. Also not recommended, by the way, because HMACs have a second signature scheme. JOTs. HMACs are only useful within one single isolated application. Everybody else should be using asymmetric signatures, which are much more awesome, but also a bit harder to implement. But you should go through the effort of doing that. What's going to happen here is we're going to use a signature algorithm, again, a dedicated cryptographic function, and we give it a data and a private key, and out comes a signature, which we add to the data, and we push it out to the client in this case. And when it comes back, we get the data and the signature. And we use, again, a specialized function to verify that signature, which takes the data and the original signature as input, along with a public key. And it will tell you yes or no, true or false, exception or no exception, depending on how it's implemented. And when it's the same, when it's a go, thumbs up or whatever, that means that the data has not been changed and that the data has been signed by the private key belonging to this specific public key. And when something doesn't match, either the data changed or it was signed by a different key, honestly, we don't care and we don't want it. And this mechanism is much more beautiful to use. Because this means if you are issuing JOTs to all the conference attendees, all you need to give them is your public key. And the word says it itself, public key, everybody can know that. Because nobody can use that to generate valid JOT tokens in your name. The only thing that can do that is a private key, which, as the word implies, you keep private. You store that in your key vault, and you give nobody else access to that private key. And that is how you handle JOT signatures. And this is the only useful thing in most applications. Even within your own trust zone, even within your microservice architecture, every service issuing JOTs should have their own private public key pair, allowing you to compartmentalize that, allowing you to verify who actually generated this JOT and whether you want to trust that yes or no. Very, very, very important, and again, something that I often see implemented in a different way. All right. One of the reasons JOTs are so hard is because they're crypto, basically. It's not about JSON, no, it's about signing and encrypting. Whenever you sign something, think about our scenario we had here. Our friend up front, which is totally going to hate me for targeting him, is giving all of you a JOT. It's giving all of you a JOT, and you want to verify that. How do you know his public key? You don't, right? That's going to be a hard problem. And the same happens in an architecture. You need to get hold of the right key. One simple way would be for him to add his key to the wall of keys. Let's say we have a wall of keys here, and he gives it an identifier, like my key is number 17. So now you can include a claim in the header of your JOT called KID, the key identifier. And in the case here, it would be 17, allowing you to go to the list of public keys. 17, oh, that's the key I need to use, and you can verify that JOT. So if you have a bunch of keys floating around in your organization, you can go to your key vault and ask the key vault, like, hey, give me the public key with ID 17, and off you go. Or a long and random UID, which is a bit harder to pronounce in a presentation, but realistic as implementation. All right. That's very nice if you have a centralized way to access keys. Doesn't work very well in distributed scenarios. Let's say Google is issuing JOTs and I need to verify them. Well, there's probably not going to be a very easy way for me to grab Google's public key in a reliable way, which is why the spec has some other mechanisms as well. They have a GKU claim, and a GKU allows the issuer to embed a URL holding a set of public keys. They're represented in a JSON format, which is absolutely ugly for public keys, but doesn't matter. You never have to look at it as a human, so we're all good. But essentially, here's a JSON web key set, a set of public keys. I can fetch it from there, and then the key identifier is going to say, like, oh, from those keys, just use the key with this ID, and I can now verify the signature. And if Google decides to start using new keys tomorrow, they just publish the public key on that endpoint, change the KID in the next issue JOT, and again, my service can go there, fetch the keys, verify the signature, and trust the data coming from Google. All right. If you don't like JSON web keys, you can also do the same with certificates, X509 certificates. There you would use the X5U claim, you give it a URL pointing to a certificate, and you can fetch that key information from there. That's essentially how key management works in a JOT world. This is something that I've honestly never seen implemented in a real-world system. People think about this, then they don't do it, but you need to implement key management. But you need to be careful with that. Because once you start doing that, you'll end up with a scenario like this. Somebody gives you a JOT. It's signed by a private key, so you need to verify that with a public key. And you can find the key set, the JSON file with keys, on evil.example.com. Like, Your application has been implemented because you listened to like half of this talk and not the other half. So it's like, oh yeah, so the GKU, I'm going to fetch those keys. I'm going to find the key with this identifier, like this KID. Oh yeah, I found it. Verify the signature. Oh, it's valid. Awesome. So you're Philippe. I'm going to trust you and give you access to my account. This is not good. The problem here is that you're using information from a signed JOT without the ability to verify the signature. You're relying on this header info, but you don't know whether you can trust the JOT yet, which is kind of a chicken and egg problem, which doesn't have a good solution. That's why specs that rely on this, like OpenID Connect, have an out-of-band configuration channel. If you choose the sign-in with Google on a website, in the end, that website is going to receive a JSON web token signed by Google saying who you are within the Google ecosystem, your account with an identifier and a name. But the application is not going to dynamically fetch Google's keys. No, when you configure your application to allow login with Google, you tell it that you want to log in with Google, and the service, the libraries are going to go to this location, .wellknown/OpenID configuration on accounts.google.com on a fixed hard-coded domain. And you're going to go there, and that is a JSON file with the OpenID Connect configuration. And it's going to have a GWKS URI claim telling you like, oh, the keys for Google or this identity provider I'm using for Auth0 are located in this specific location. And you can fetch those keys before even having received the first token, an out-of-band configuration channel on a trusted location, because you point specifically your application to Google. And that way, you can sidestep this whole trusting the key thing. I'm not saying this is the only way. I'm saying this is a fairly straightforward way to sidestep that whole trust issue. Something to definitely keep in mind in real-world applications. All right. Enough about JOTs now. Well, I would say it's going to be better now. No, let's talk about cookies. Everybody loves cookies, right? No. This is the PHP era. PHP session ID, well, hopefully not 42, but this meaningless identifier. This long identifier with some entropy in there, but whatever, you get the idea. That's the old way of doing things, something that most people absolutely hate, because cookies have a very, very bad reputation. The modern way is using an authorization header. So many applications today are using the authorization header with bearer as a type of authorization value and then a token. You can recognize the EUIJ, that's the base64 encoding of a JSON object to start at least, so you know it's probably going to be JSON, in this case a JOT. Those are the two approaches. And I often get asked, like, what should we use, cookies or tokens? And I'm like, that makes no sense. Because a cookie is a mechanism to transport data from a client to the server, and the authorization header is the same thing, but what you put in there is a string. It's a text-based value. You can put in there whatever you want. So why not put your JOT in a cookie or your identifier in an authorization header if you want to switch it up? And people always look skeptical with this slide, like, what the hell is he talking about? Like, nobody does that. Well, this is an identifier. If you're using OAuth, you have a concept called a reference token, which is an identifier to state kept by the authorization server on the server side. It's called an access token, but it's just a random ID. And if you're using OAuth, you also have the JOT-based tokens, access tokens, that's called self-contained tokens, but nobody tells you what to do with them. The spec is even like, once you have that token, how you contact the server with that token, that's your business. We don't care about that. And there's actually pros and cons to all of these. Let me show you a few highlights of things that always come up. Let me first ask you, who here is using cookies with their APIs? Like nobody. Maybe I should have asked the baseline first, who's building APIs? Like, oh, okay, we're good. If like nobody raises their hand, then of course the other talks must have really been not interesting, I would say, but awesome. Many people don't use cookies with their APIs. Like, no, we don't do that. But I've seen a lot of systems that are hosting resources, at least in a web application, hosting resources that require authorization checks. For example, if you're loading images or documents or whatever, images with an image tag, you might want to enforce some authorization. If this is per customer or per project or per user, you need to make authorization decisions before giving out that image. If you don't do that, by the way, you have an insecure direct object reference problem. Skip back 30 minutes and look at that again, because that's exactly the problem you have there. But guess what? If you're loading an image tag in a web application, the browser doesn't send custom authorization headers with bearer, and your application cannot send that either unless you do some really dirty workarounds. Guess what the browser does send when you add an image tag to a page? Cookies. If you have a cookie for that domain, the browser is going to send that cookie along. And I've seen a lot of people go towards the header-based approach, like, yeah, we're going to implement this authorization header in Angular with an interceptor, and it's awesome. And then, a couple of months later, they're implementing resource loading, or lazy loading for admin templates or whatever, and they discover that there's no information there. And what they typically do is they come up with a hybrid mechanism, like, let's add a cookie to the application for these cases with some authorization. It's like, think about this up front. Same thing for WebSockets. Opening a WebSocket, you type, well, you write JavaScript code, new WebSocket something something. No authorization header, but if there's cookies for that domain, the browser will send cookies to that backend. And that might be a very good way to implement authorization. I fully agree that in a non-web world, cookies have no place. If you're building something that's not a web application, absolutely get rid of cookies 100%. But if it's a web app, think about this up front. Think about the pros and cons. I have a nice overview slide here of the pros and cons. Both headers can contain string-based values. Whatever you want can be in that header. Keep that in mind. Cookies only work well with a single domain. That's how cookies work. While the authorization header, you can send it anywhere. Contacting 10 APIs on 10 different domains, probably want to use authorization headers and not cookies. Cookies are handled automatically by the browser, which is both a good and a bad thing. But the authorization header requires you to write custom code, which might mean you introduce some vulnerabilities. And then finally, cookies are always present in a web world. Cookies are added to DOM resource loading, to WebSockets, to cross-origin calls with XHR if you enable that, while the authorization header is only there when your application is in control of that request. If you're sending it from JavaScript, sure, you can add it. Otherwise, you'll need either a very dirty workaround with service workers, which is not recommended, or there's no information there. And that's the truth about this. Cookies in a web world are the only thing that work really well because the browser handles them automatically. Again, when I talk about API security in courses, my disclaimer is I have no answers. I only have options. I can give you the options. I can tell you what to look for, but the final decision is up to you. You decide what's going to work for your application. And honestly, in this case, both of them work quite well. That takes me straight to one of my pet peeves on security. If you're writing something with an authorization header, you are writing application code to make it happen. You are writing code to take something out of a response from the server, store it somewhere in the browser, and reattach it on an outgoing request. And one of the questions you will have is, where do I store this thing? Where do I put it? Like in the browser, where would you store things? Like there's local storage, session stored in IndexedDB, and so on and so on. It's like in memory maybe? Who knows? It's a really, really difficult problem. And a lot of people struggle with that. And you'll find advice online telling you to be really careful, because if you put it in a local storage, you'll risk cross-site scripting attacks. If the attacker injects some JavaScript in the application, they can read everything that's in local storage and ship it off somewhere else. And if that thing was a token that's valid for 8 hours, the next 7 hours and 59 minutes are not going to be very fun for the user whose token got stolen, which is a problem. And some people have solutions like, you know what? We have something called HTTP-only cookies. So we can put it in a cookie and then mark it HTTP only, meaning that JavaScript is not allowed to read it. And that takes away that danger, right? These are HTTP only cookies. It depends on where you're standing whether this is secure or not. From the outside, it's like, oh yeah, the door is locked, until somebody pushes that and off you go. Because the problem is not the fact that you hide a value, the problem is that you're running code from the attacker. That's the real threat. Cross-site scripting means game over. And this is something that comes up over and over again. People, this is a tweet from me from last year. I usually don't go looking for these things and calling people out, but if they ask me, like, can you look at my blog post, and I have some time, I'll do it, but I'm gonna tell it like it is. This is bad advice. Because yes, hiding this token from an attacker in cross-site scripting seems to solve the problem, but it only sidesteps, it addresses one symptom, and that's it. You're still running code from the attacker can still do whatever they want in the application. They can change the UI. If you're building a banking app, they can add transactions to the list of transactions to do and hide them in the interface. The user will not even know that the transaction is there. The attacker has already won. So hiding one little token, yes, it's gonna make it harder to attack your application. That's true. It means that your 8-year-old script kiddie that broke in is not going to be able to exploit that. They'll be like, oh, there's nothing in local storage, let's move on to the next one. You got away good there, awesome. But a real attacker, a skilled attacker, a pen tester is going to be like, okay, let's see what you're doing. Oh, I can start making API calls, I can do whatever I want. If you're using OAuth, they can embed an iframe and get a new access token that way before it's hidden away in memory or HTTP-only cookies or whatever. It doesn't solve the problem. So my advice is do not ever underestimate cross-site scripting. And instead of looking for like the best place to put this little value in the browser, spend that time learning how to prevent cross-site scripting in your application. Much more useful, because that's the real problem, not the hiding of this value. Who's building Angular frontends? Awesome. Angular solves most of cross-site scripting issues for you. Look on my website, I have some advice on Angular. Who's building React apps? Yeah, bad news for you guys. React is not really good at preventing cross-site scripting, so I built a full one-page cheat sheet on how to do that correctly. Again, go to my Twitter feed, you'll find the cheat sheet, it's freely available, you can download it today and start using it on Monday at your job to look for cross-site scripting in your React apps. If you have questions, I'll be around the rest of the day, so you can harass me after my talk as well. All right. Are we still good? Should your API accept this input? It's like, ugh. That is one unfortunate username. Probably not. I don't know, maybe not. There's a 1 here, so probably you actually want a numerical value, so this is bad input. And many people talk about this in the first steps, like input validation. Oh my God, you need input validation. I don't, but I'm talking about it now, towards the end. Lack of input validation is absolutely a security problem. You need to have input validation. Input validation gets rid of known malicious data. If you get 5 megabytes of password data, probably not a real password, just saying. Yes, 25 characters, 30 characters, that's acceptable, so cap it at 100. But everything larger than 100 characters is trying to DDoS your server by sending you large passwords. Reject that. However, input validation will never be your full defense. Should your API accept this data as input? No. Some people say no. Some people are like, huh, that's interesting. Well, it depends. If you didn't accept the first one because it was SQL injection, then you shouldn't accept this one either because it's SQL injection. However, if you're relying on input validation, you're going to have a bad time. First of all, this is a valid email address. So if you input validate this with an RFC email address validation library, it's going to be like, yeah, totally valid. If it causes SQL injection problems, you have bigger problems in your API. Because input validation is never going to be your only or primary defense. Input validation can never stop things like SQL injection, command injection, cross-site scripting. It can only get rid of known bad data to keep the crazy out. That's why we have these guys at the front door checking your badge when you come in. Input validation. If your badge is missing, they'll be like, oh, you're not allowed in here. But of course, everybody with a camera and a scanner or a printer can actually create a badge that looks good enough to get in anyway. We have no other security here because everybody should learn about security development. But input validation will never save your butt for security. It's good as a first line of defense, but never as the only defense. Keep that in mind. You should have it, but it will never save you from the actual attack. That's why we have parameterization for SQL queries, why we have output encoding or standardization for cross-site scripting, escaping for command injection, and so on. The real defenses happen at output time, not at input time. Very, very important consideration. All right. Final takeaway. What happens when chocolate ice cream goes wrong? No, not even my kids think this is ice cream. So apparently it was supposed to be ice cream, but that failed miserably. Not sure whether a different color would have helped. That would have just... Anyway, things go wrong. Well, hopefully you'll never have an issue, but in reality, you're likely going to have a security issue at a certain point in time. It's going to happen. So the best thing you can do is think about this up front. Like, what if something goes wrong? And one of the best defenses that you can use is compartmentalization. Split things up into smaller components. If you're building an API that serves a public part of an application and an authenticated part and an admin part, that should not be one API. That should be 3 separate APIs, preferably running on 3 separate subdomains or domains or whatever, because that helps you compartmentalize. That means if something goes wrong in the public part of the application, it's going to be separated from the other parts. It means you'll be able to detect cross-application or cross-trust boundary communication and reject those requests immediately. And this is something that holds for both back-end systems and front-end systems and so on. Always try to think about these things and reduce the impact. And today you can build very seamless user experiences even with multiple compartmentalized applications working as one big application. So always keep that in mind because this is the thing that's going to save your butt one day. Oh, a vulnerability in our front page which is public without authentication. Whoops, let's fix that. But if we compartmentalize that from the authenticated part, authenticated users will not suffer from that vulnerability or suffer less. And that is going to be really, really important. Question everything. Don't just do something because you wrote one blog post that says that's how you're supposed to do things. Question what I'm saying. Ask me those questions and I'll try to argue with you on why I'm right. Usually I am. Sometimes I'm not. But that's why I only talk about security, not about other things. But seriously, question these things. Healthy debate is useful because you need to understand the different viewpoints and the nuances to be able to make accurate security decisions in your applications. All right. Thank you very much for listening. Grab the slides and the cheat sheets from Twitter and ask any questions you want to right now or the rest of the day at the conference. Thanks for being here.